Okay, I'd like to finish up section 6.2 here, and we're on problem 16. To find the mean and the standard deviation of a binomial random variable, here's the formulas that you use to get mu sub x and sigma sub x. So let's take a look at problem 16. It says, according to the American Lung Association, 90% of adult smokers started smoking before turning 21 years old. Let the random variable x be the number of smokers who started smoking before turning 21 in 200 trials of the probability experiment. Okay, in the last video, we had already talked about why this is a binomial experiment, right? Because the four conditions are satisfied there. In part A, we want to compute the mean and the standard deviation for the random variable x. Okay, so because this is binomial, we're going to know n and we're going to know p, and we just multiply those two numbers together to get the mean. The mean is 180. Now, I think that should make total sense to us because think about it, if you were told that 90% of smokers started before turning 21 and you had 100 smokers in a group, you would expect 90 of them to have started before turning 21. Well, here I'm just doubling that then, right? 90% of 200 is 180. The standard deviation, we want the square root of n times p times q. Q is 0.1. If you take 1 minus 0.9, you get 0.1. And 200 times 0.9 is 180, times 0.1 is 18. The square root of 18 would be roughly 4.24 if you go to the nearest two digits. Okay, so there's not a huge spread in the data from that number not being, you know, a super huge number. Now in part B, it says, would it be unusual to observe 165 smokers who started smoking before turning 21 in a random sample of 200 adult smokers? Yeah, that would be very unusual because, as I just mentioned, there's not a huge spread in the numbers. The numbers really only stray from the mean by about 4.24 units, okay? So they'd want us to see that 165 is pretty distant from 180 when you consider the standard deviation. Now in part C, would it be unusual to observe 185 smokers who started smoking before turning 21 in a random sample of 200 adult smokers? No, that would not surprise us because 185 is very close to 180. You're just a little bit beyond one standard deviation to the right of that number. Okay, so that would not be unusual to us. Now, obviously, the thing to see here is the standard deviation, and that number, how big or small it is how we're getting our yes/no answers. If I had computed the standard deviation to be like 14.24, then no, it wouldn't be unusual to observe 165 smokers who started smoking before turning 21, because you know, you'd be a little bit, you'd be within one standard deviation of the mean then. So again, the standard deviation is the key thing in this problem. Part D, we want to use the calculator to find the probability that in a random sample of 200 adult smokers, 175 of them or less started smoking before turning 21 years of age. Okay, 175 or less means that X could be 175, 174, 173, 172, right down the list, all the way down to 3 or 2 or 1 or 0. Okay, now I wouldn't want to find 176 probabilities using the binomial probability formula. That would be very brutal and time consuming. So they intend for this to be a calculator problem. Okay. Here's how you would do the calculation with the 8384 model. If you hit second and then the VARS button, and then go down to where it says binom CDF, you'll enter in n, comma, p, comma, x, and it's got to be in that order. So n is 200, comma, the p-value is 0.9, x is 175, and that's how I'm getting this number here that I've got rounded to 4 digits. Okay. On the Inspire model, if you have that, you're going to turn it on and hit Calculate, and you'll just hit Menu, go down to Probability, and then over to Distributions, And then you want to scroll down to where it says binom CDF, hit enter. The number of trials is 200. The p-value is 0.9. The lower bound, you're going to keep that as at 0. And 175 would be the upper bound, since we're looking at all 176 numbers that are going from 0 to 175. And then hit OK, and you'll see that the probability is the same number that I was getting there on my sheet. Okay, now obviously in a situation like this, the calculator would come in handy. But this would be how you'd calculate like several probabilities, if it were a less than or equal to situation. Okay. Problem 17 is the last one that I had here on the worksheet. It says, according to the manufacturer of M&Ms, 20% of the plain M&Ms in a bag should be yellow. And just as a random useless fact, that's actually regardless of the size of the bag. If you have a regular size or a fun size or a big bag, the manufacturer wants it to be so that 20% of the bag is yellow M&Ms. Now, of course, it's not always going to be 20%, but that's what they are aiming for, in the factory when the bags are made. Suppose that 5 M&Ms are randomly selected from a bag and the number of yellows is recorded. Let the random variable x represent the number of yellows in the sample. Okay, this would be a binomial experiment since the 4 conditions would be satisfied. N is 5. Remember, N is usually just the sample size there. We would have independent events because just because you get a yellow M&M on the first selection, that has no effect over the next M&M being yellow. Okay, you're only going to have 2 outcomes. Either the M&M is yellow or it's not. That's all we care about is the number of yellows that we get. And then the probability of a success would stay the same from trial to trial. That's condition 4. That would be true here because we were told that 20% of the M&Ms in a bag should be yellow. So that's regardless of the selection, you always have a 20% chance of getting a yellow M&M. Okay, and that's not going to change. So part B, then, we're going to compute some probabilities now. What is the probability that exactly 3 M&Ms will be yellow? Okay, so I'm using my binomial probability formula. X is 3, N is 5, P would be 0.2 since 20% of the bag is yellow, and Q would be 0.8 since 80% would not be yellow. So I'm going to want 5 choose 3 times 0.2 cubed, x is 3, and then 0.8 squared, n minus x, or 5 minus 3 gives me 2. Remember, the powers of p and q, when you add those, will always give you n. That will always happen. So then I go to the calculator and simplify. 5 choose 3 is 10. And 0.2 to the third is 0.008, and 0.8 squared is 0.64. All 3 of these numbers would be exact, so I'm fine with using the equal sign there. And when you multiply these 3 numbers, you get 0.0512. Okay, and again, that's an exact. So there's a 5.12% chance that 3 out of the 5 M&Ms would be yellow M&Ms if it were a random selection there. Okay. By the way, when it comes to the rounding for the problems that are in this section, I've noticed that the book is usually going out to 4 digits in the answer. So consider that when you're giving the answers on My Math Lab. Of course, pay attention to where they're rounding in general. Part C, what is the probability that at least 3 M&Ms will be yellow? Okay, at least 3 means 3 or more. So that could mean that x is 3 or 4 or 5. So I've got to compute these 3 probabilities. We've already got the first one done. That's what we did in part B. And so now what if we get 4 yellow M&Ms? X is 4. It's going to be 5 choose 4 times 0.2 to the 4th times 0.8 to the 1st, or just 0.8. And then when x is 5, it's going to be 5 choose 5 times 0.2 to the 5th times 0.8 to the 0. Okay, the first probability I've already just I've just rewritten that there. 5 choose 4 is 5. 0.2 to the fourth is 0.0016, and then times 0.8. 5 choose 5 is 1. Remember, anytime you've got n choose n, that's always 1. Also, anything to the 0 power is 1. Okay. Now, on this one, so all we have to do is type in 0.2 to the fifth. And 0.2 to the fifth, if you were to hit enter on the 83, 84 models, you'd get some scientific notation deal. 3.2 e negative 4 just means that you're going to slide the decimal point 4 places to the left. And so here would be the number in standard form, 0.00032. Sometimes in probability you work with very small numbers, and so that the scientific notation comes up not a lot, but here or there, and it just indicates where the decimal is going to be moving to the left, how many places there, of course. So then I multiply these 3 probabilities together, and looks like there's a 5.792% chance that you'd get at least 3 M&Ms that are yellow in a selection of 5. That seems pretty unlikely to happen with that being such a low probability. Okay, and go to the next page here. Part D, what is the probability that fewer than 3 M&Ms will be yellow? Okay, so fewer than 3 means that x has to be less than 3. So x could be 2 or 1 or 0. Now, rather than computing 3 probabilities, which I could do if I want, why don't we just use the complement rule? Okay, the opposite of fewer than 3 is to have 3 or more. And we just found that probability in the last part there. It was 0.05792. And so I guess to get the answer to part D, all I need to do is subtract that number from 1. And it looks like we have a 94.208% chance that there's going to be fewer than 3 yellow M&Ms in the group of 5. Okay, so that seems very likely to happen with that probability being so high. Now, if I were to compute 3 probabilities there, so like when x is 2 or 1 or 0, I would still get the same answer. That would happen, okay, but consider the times where you can use the complement rule if you've got information already computed earlier. That would be the faster approach, of course. Part E, what is the probability that between 2 and 4 M&Ms inclusive will be yellow? Okay, inclusive means that I'm including the endpoints. That's a key word because if they did not say that word, being between 2 and 4 just means that x is 3. So I need to compute 3 probabilities, not just 1 probability. I've already started to do that here. I've got I've already computed when x is 3 and when x is 4, so really I just need this first probability. 5 choose 2 is 10, 0.2 squared is 0.04, 0.8 cubed is 0.512. The rest of this we've already found from earlier from our work in part C. And when I simplify, I'm getting 0.2624. So it looks like there's a 26.24% chance that between 2 and 4 M&Ms inclusive would be yellow if it were a random selection of 5 from the bag. Okay, this is a problem that I would have done with you guys in class, and I usually bring in a bag of M&Ms and pass out a bunch of like fun-size M&Ms, and so I've got a fun-size bag of M&Ms here. I'm going to open the bag and select 5 random. I try not to look when you do that, and so okay, so there's my 5 that I've randomly selected. I've got 1 yellow M&M, as you can see. Okay, now how likely was the sample? Well, I usually have in class, usually nearly half the class gets either no yellows or 1 yellow, or I might have like 1 or 2 students get 2 yellows. Okay, that's pretty likely to happen since from our calculations here, we have a 94.208 chance of getting fewer than 3 yellows. Okay, that's very likely to occur. It is very unlikely that you would have 3 or more yellow M&Ms. Less than a 6% chance of that occurring. That's very unlikely to occur. Okay, so we can see that here from this bag in the colors that we were getting. Okay, and then part G, compute the mean and the standard deviation for the random variable. This is binomial, so to get the mean, I just simply take n times p. N is 5, p is 0.2, 5 times 0.2 is 1, which means that on average we would expect one yellow M&M to be selected in a group of 5 if it were a random thing. That's exactly what we see here. And the standard deviation is the square root of n times p times q. Okay, 5 times 0.2 is 1, times 0.8 is 0.8. The square root of 0.8 is 0.894. That's not a huge spread in the values. Okay, so while the average is one yellow M&M, like it wouldn't be unusual for us to stray about 0.894 units away from that number. Like it wouldn't be unusual for x to be 0 or 2, since 0 and 2 are roughly 0.894 units away from 1. And that would be very likely to occur, as we mentioned earlier. All right, so that is all I had in Chapter 6. We're now done with Chapter 6. Here's the homework in Section 6.2 that I'd like you to look at on page 320.